So the next problem we have on our exam is this, oops, there we go, is a rubber elasticity problem, although I'm going to give me a better title, but we have an elastomer. An elastomer means we have basically a rubber elastic material, so we are not going to use our traditional kind of stress strain tensors. We're going to have to use our rubber elasticity, and in rubber elasticity we know that alpha 1, we're dealing with incompressible material, alpha 3, our extension ratios are all equal to 1. So we're also given here that the Young's modulus is 411 kilopascals, and then this is at room temperature, so T is equal to 298 Kelvin. We're also told, for this particular problem, that, well, now we could actually say, so my Young's modulus is equal to 411 times 10 to the 3, and this is equal to n sub x k times t. We know k is our Boltzmann's constant, so we could actually solve for n sub x right now if we wanted to, and why not? Because we could show off our knowledge. So I'm going to quit my kernel. I am going to just solve for this. So solve 411 times 10 to the 3, set this equal to 1.38 times 10 to the minus 23, and then x times basically 298. And close it up. And what do we get? Something on the order, so our n sub x is on the order of around 10 to the 26 number of polymer chain, or number of crosslinks per basically meter cubed. So we're also told that the magnitude of the force in the 3 direction per polymer chain is this, that newtons, and there are 2 directions. In the 2 direction is 2 orders of magnitude less. So now I can see here there's going to be a stress in the 2 direction, and then a stress in the 3 direction. So when I'm looking at I want to keep everything general. So we have this following expression. So delta S equals minus K over 2 times alpha 1 squared plus alpha 2 squared plus alpha 3 squared minus 3, and that my force in the I direction equals minus T times derivative of S, or delta S, over dLi. So if I have that, now I can start to go ahead and solve and basically solve these problems. So I know I'm changing the alpha 2. So alpha 2, there's some new distance in my L2. There's also going to be a change in my alpha 3, and then in the 1 direction, there's not really a force there. So I can write alpha 1 in order to make sure that this is conserved. If this exists and this exists, then my alpha 1 must be equal to 1 over alpha 2 times alpha 3. So I can start to kind of write out these values, and what do you know? Oh, my Mathematica really is crashing on this computer. But we will kind of live to see another day. So let's go ahead and let's boot it back up, open up my welcoming screen. I think it may be because I'm recording as well, but anyways, it really gives us a perfect opportunity. So my delta S, actually let's go ahead and zoom in again. So my delta S, or I'm just going to say ds. ds is equal to minus k divided by 2 times, minus k divided by 2 times alpha 1 squared plus alpha 2 squared plus alpha 3 squared minus 3 here. So that's my ds. And then I'm going to define, actually above here, so alpha 3 equals, alpha 1 equals basically 1 divided by alpha 2 times alpha 3, and we also know that alpha 2 equals the new direction in 2, L2 naught, and then my alpha 3 is equal to L3 divided by L3 naught. So got those values, plug that in here as well, plug that in here. So now I could do my force in the 2 direction, F2, is equal to the minus T times the derivative of ds with respect to L2. And my F3 equals minus T times d ds with respect to L3. So those are my forces in the most general term. So I know what my L naught 2 is. I don't know what my L naught 2, I do not know what my new length in 2 direction is. I don't know what my new direction in the 3 is. So I could ostensibly kind of start to do that now, but I also know they're going to be asked for stress. The stress in the 2 is going to be Z, my number of basically cross-links or polymers, essentially, times F sub 2 divided by my area, which is going to be L naught 1 times my L naught 3. So I can plug in, and we have an extra expression. We know that N sub X is equal to Z over my volume, my V naught. So the volume of my material. So I could solve for Z right now. So I could just say that, because we solved for it previously, we said my NX is 10. So I could do it and solve that my NX, let's see here, I solve that my NX, so it's 10 to the 26 approximately, set that equal to basically our Z divided by my volume is basically 5 times 10 to the minus 3 times 5 times 10 to the minus 3 times 500. So 5, control, control, control. So that is 500. So I could figure out what Z is. So that would be, I could set that equal to Z. So let's go ahead and put that in right in there. So Z is equal to this. So I could now kind of go about and solve the rest of these problems. So let's first solve for F2 and F3. So my Boltzmann's constant is equal to 1.38 times 10 to the minus 23. My temperature, so my temperature is equal to 298 K. I think we're at room temperature here. Yes, we are. So let's look at F3 now. So all I have left is actually let's define that L sub naught 2 is equal to 500 millimeters. And my L naught 3 is equal to, let's see, L naught 3 is equal to 5 millimeters. So there we go. And now we can just do simply, let's look at F3. Oops. Or L3 naught, excuse me. L2 naught, L3 naught. So now we're just left with L2s and L3s. So I need to solve, and we said that our force in the 3 direction was 6.5 times 10 to the minus 19. So 6.5 times 10 to the minus 19. Set that equal to F sub 3. And that we're also told that in the 2 direction it's 2 orders of magnitude less. So let's go ahead and solve there, solve there. So minus 21, and that's F sub 2. Let's solve this for L2 and L3, and we'll solve that for the reals. So I don't want any negative values, can't have any negative values. So my L2 is equal to 0. Is this. So that's my L2. My L3 is this. L3 is equal to this. So what is my alpha 1? This. My alpha 2 is this. My alpha 3 is this. So I've got my, basically those values here. So alpha 1, alpha 2, alpha 3. So I've got my extension ratios. I've also got, let's just make sure those are those values right here. So L naught 2, so those values here. Yep, your alpha 1, alpha 2s, alpha 3s. So we've got those in there. And now we can start and actually work with these other values as well. So now let's go ahead. So we've found the extension ratios. We need to do the stress now. So my stress in 1 equals Z times my F, actually stress 2. Let's do stress 3 is F3. So we look at F3 now. So that's my force per pound, my force 2, that, excellent. So divided by my area, which is L naught 2 times L naught 1. What is my L naught 1? Well, my alpha 1 is this, so I need to solve. I know that this is equal to, actually I do know what my L naught 1 is equal to, let's see, in the direction there, it's equal to 5 millimeters. L 1 equals 5 times 10 to the minus 3. So we got that. So now I can do L1 divided by L naught 1. So there's my L1 just in case we needed that. So this would be my stress. This would be my stress in the 2 direction, would just be Z times F2 divided by L naught 1 times L naught 3. And there we go. We've gotten those values. So if you look at it, our basically extension ratios were equal. So again, the stresses were, basically equal there. So that's our values here. So we've got the stress, we've got the force, because I could just look at F3 and, again, we got those values. Or I could just multiply out by the volume. So I could just do Z times F3, which would be my total force, Z times F2. So now, write the full stress and strain tensors. So in this problem, there's only going to be, basically, for my stress tensor, there's only going to be stress in the, there's no stress here, stress in the 2, 2, which is my 2 direction, 3, 3. So we have those values. For strain, we need to now look at our alphas. So my alphas, if I look at my L3 minus L3 naught, so my strain in the 3, 3 would just be this divided by L3 naught, 3 naught. So there's my strain in the 3 direction. What about my strain in the 2 direction? 2, 2, 2. So we got that variable here. And then finally in the basically L1, which we found to be what? Right here. So my L1 is equal minus my L1 naught. L1 naught. Where's my, or L naught 1? L naught 1. Ooh, actually, I think I really need to be careful. I think I could have made a little bit of a mistake here. L3, L2 naught, 3 naught. Let's just make sure my alpha is equal to L2 naught is what? 0.5. Yes, that's true. What about my L3 naught? Again, I think I have those values correct. All right, so continuing on. So I'll get this divided by L naught 1. And we could double check L naught 1. Yep, makes sense. So again, you could see that the strain is negative here, which makes sense because if I pull in the other direction, these should be positive strain, positive strain. They have the same, stress values. And then I've got this. So that would be my strain tensor will just be epsilon 1, 1, epsilon 2, 2, epsilon 3, 3. That's it. Those are those values. So now we're on to question number 3.